This video will be on section 4.2, second derivative and concavity. So the two things we'll talk about are exactly that. We'll talk about the second derivative, and then we'll talk about what's related to the second derivative. It's called concavity and points of inflection. Even though we'll talk about it when we get there, one thing I'd like to point out, this section is very, very similar to section 4.1 in that concavity is like figuring out where the graph is increasing and decreasing. And points of inflection are like critical numbers. So just to preview that, because when we get there, we'll see that really the questions in this section are not any different. There's just one extra step. All right, but first thing, the second derivative, what does that mean? Well, simply put, the second derivative of a function is the derivative of the derivative. All right, so we've done a lot of derivatives in this class, and if you look back on any of them that we've done, you always get a formula, another function for the derivative. So if you do the derivative of that result, then what you have is the second derivative. And you're actually allowed to do as many derivatives as you want in general. You never have to stop. As far as applications to business and even in the sciences and stuff go, you don't often go farther than the second, maybe third or fourth in some very rare examples. All right, but we just have two examples here computing the first and second derivatives of each of the following. So the first one, h of x equals 4x to the negative 5 minus 9x to the negative 6. Right. The first derivative, we just do the derivative of each part like we've been doing for a long time now. We get negative 20x to the negative 6 for the first term. Bring the negative 5 down, subtract 1 from the power. Just do the regular power rule. Minus. And then when we do the negative 6, bring it down with a negative 9, we actually get a positive 54x. And then the power, subtract 1, we get negative 7. All right, now all you have to do the second derivative is do the derivative of this one. All right, so just like I wrote and said above, you do the derivative of the derivative. If for the first couple times you do this and there's just a little something that's a little off, a little confusing, pretend this is your original function. Just kind of hide the prime there and just do the derivative of that. Right, so we're not going to deal with this function anymore, at least for this problem. This one's pretty much gone for us. So the way we symbolize the second derivative is a couple ways, but this is the most common way and the only way we'll use because the other way is more convoluted. You just do 2 primes to indicate second derivative. Now, if you continue this pattern, you do like the third and fourth and fifth and sixth derivative, eventually there's too many primes. If you want to do more, you don't have to in this section and definitely in this problem. But if you want to do more derivatives, let's say, you wanted to do 10 derivatives, you wouldn't want to write 10 primes. The notation we use is h, and then we put a parentheses with the number inside. Make that more clear. N of x. The number with the parentheses inside means do the nth, that is the nth derivative. All right, but if you don't put the parentheses around it, then it just means do the function to a power. So you won't really see that. You might if you read parts of the book, but we won't really see that in the homework. Anyway, back to our problem. We do the derivative of this. Bring negative 6 down, we get positive 120x, subtract 1 from our power to the negative 7, and then plus 54, we do the power rule here, bring the -7 down. 54 times -7 is negative 378x, and then we subtract 1 from the power, we get -8. Now you may have corrected it as you went, but the only thing to simplify here is just the plus and negative, make it a minus, and that's all you need to do. All right, so really what we're going to be doing in the second part and in most of this section is we're going to do the second derivative. That's what's going to be related to this concavity and points of inflection stuff. And then we're going to figure out the concavity and points of inflection exactly like we did increasing, decreasing, and critical values of the last section. All right, so that's really going to be the only difference. All right, now this next one, I really, like to do this example because when you do more than one derivative, the process, the rules you do can change. The first one we did here, we just used the power rule for each one. We didn't have to do anything extra. But the second one, we'll notice a difference. All right, so here we want to do the derivative of f of x equals x squared plus 6 to the 9th power. We know we're going to need the chain rule for that. So we bring the 9 out front. Right, we keep the inside the same. So we start with the power rule, subtract 1 from the power, and then we multiply by the derivative of the inside. The derivative of x squared plus 6 is 2x. And I know that some of you may be very comfortable with the chain rule, but it's always good to point out why we have this extra thing, just as a reminder. And you probably won't see a ton of problems in this chapter with the chain rule because we have so much extra stuff to do. But you don't want to forget that you need to do it when it pops up. Now what I would do is simplify this because you're going to do the derivative of this. All right, the general rule of thumb, like I've been mentioning as we go along, if you need to do anything with the derivative, whether it's, like previous sections where we figure out where the derivative equals 0, or in this example, when we're doing another derivative, you need to simplify, get rid of any negative exponents, unless if it's like this, because this one was straightforward, and then do the second derivative. But the only thing to simplify here is 9 times 2x is 18x times x squared plus 6 to the 8th. All right, now we want to do the derivative of this result. And what we have to do here, which did not pop up in the last problem, is the product rule. We didn't have to use the product rule here because we only had x in one spot. Now we have x in 2 spots. We have 18x times this function. So we need to use the product rule here. All right, anytime you do the second derivative, it's possible that the way you're going to do the derivative changes method. It might also say the same like we saw in the first one. And I'm just going to do it like we did before, point out the first and second parts, and then use our product rule formula. Right, so remember the product rule formula. We do the derivative of the first, so the derivative of 18x times the second, which is x squared plus 6 to the 8th, plus the first, 18x, times the derivative of the second, which is x squared plus 6 to the 8th power. And now we take care of the two derivatives. The derivative of 18x is just 18. So we got our x squared plus 6 to the 8th plus 18x. And then the derivative of this, it's just like the derivative of the first one, except we have a different power, but we got to use the chain rule. We bring the 8 down, rewrite the inside, subtract 1 from the power, and then we multiply by the derivative of the x squared plus 6 the inside, which is 2x. All right, but now let's go ahead and simplify. Even though we could stop here, this will be able to be simplified quite a bit. The first term doesn't need to be simplified at all. The second term, 18x times 8 times 2x. I don't know what 18 times 8 times 2 is off the top of my head, so let's figure that out. I open up the calculator. We have 18 times 8 times 2 is 288. We have an x and an x, which give x squared on the outside, and then we have x squared plus 6 to the 7th. And the one thing I would say here is you can factor out quite a bit. Like I said before, nothing's wrong with this answer, but you can factor out and simplify. We have an 18 in common, and the reason we know that is because we had an 18 before. So maybe you wouldn't even want to multiply the 18 times 8 times 2. We don't have anything else outside in common, but we also have an x squared plus 6 to the 7th power in common. Because each term has an x squared plus 6, and the smallest power is 7. I'm going to factor that much stuff out. And then what's left inside? In the first term, we took out everything except one of the x squared plus 6's. Since I only have one of them, I don't need to write parentheses anymore. In the second term, we didn't take out this x squared at all. We took out all of the x squared plus 6's. And 288, we took out an 18, which leaves you with 16. If you want to quickly see that, if we took the 18 out right here, we would have the 8 and the 2 left. All right, but at this point, you're almost done being completely simplified. There's nothing you can do about the 18 times x squared plus 6 to the 7th. But inside here, we have like terms to combine. X squared plus 16x squared is 17x squared plus 6. Now, once again, the reason why I just like to practice simplifying is it's a good habit, but also I believe this would be the answer you see in the homework. So if you got here, typed in something wrong, and then got it wrong and saw this, you might think you're way off. So just always keep that in mind. All right, so concavity and points of inflection. Similar in nature to the first derivative, the second derivative tells us something important. And to understand that is to see what it does graphically. So what I'll first do, we'll define what all these things are, concavity, points of inflection. I'll actually do an example, graph it, and then we'll be able to understand it from the graph. Right, so it says, let f be a twice differentiable function. This is only because we got to do the second derivative. And it says, let a be in the domain of f if the second derivative at a is negative. We say f is concave down at x equals a. And if the second derivative at a is positive, we say that f is concave up at x equals a. Right, so drawing comparisons to last section, once again, concave up is like increasing, but it's for the second derivative instead of the first. And concave, I realize I wrote the color backwards. Let me erase that just to avoid confusion. Concave down is what I highlighted in this color. Concave down is when the second derivative is negative. That's like decreasing for the first derivative. And concave up is like increasing, second derivative is positive. Is like increasing. So just drawing comparisons. So if we wanted to figure out where our functions here were concave up or down, we would have just done the second derivative of each instead of the first, as we did, and solved it the exact same way, making a number line, plugging in numbers, and checking. All right, so what a point of inflection is, like I said, that's sort of similar to a critical value. It's also sort of similar to a maximum or minimum. It says let C be in the domain of f. We say that the point C, comma, f of C, that point x, y coordinate pair on the graph of f, is a point of inflection if the second derivative is 0 or does not exist, and the second derivative changes signs at x equals c. Right, so to draw parallels from here, it's sort of like a critical value where there's a maximum or minimum, because the second derivative changes signs. All right, so remember from last section, we had a maximum or a minimum if the first derivative was changing signs. We just had to pick the appropriate one, and we had neither at a critical value if the sign stayed the same. But just keep that in mind as we work through this problem. We're going to be doing almost exactly the same thing. We're just going to be dealing with the second derivative. All right, so it says let f of x equals x cubed plus 45x squared. We want to compute all inflection points and give the intervals where f is concave up and concave down. Right, but all this stuff tells us do the second derivative. Right, so whenever you're, I always find, at least when I was learning this stuff, that's the thing I wanted to always remind myself. There can be a lot of little things going on in this chapter 4. The way you want to just separate the first and second sections, concavity, do the second derivative. All right, so do the first derivative. The derivative of x cubed plus 45x squared is 3x squared plus 90x. Right, this is useless as far as what we're doing here. The second derivative, we do the derivative of this, and we get 6x plus 90. And this equals, well, that's the second derivative. Now, one thing you're not going to get right away are the inflection points, because like with the maximum or minimums, we have to make the sign chart first. But what we want to do is set equal to 0 to find potential inflection points. Okay, so 6x plus 90 equals 0. Let's solve that. For x, we subtract 90 on each side. We get 6x equals negative 90. And divide by 6. And we get x equals negative 15. All right, this is our only potential inflection point. These are like the partition numbers from last time. So what did we do with the partition numbers from last time? We made a number line. We're going to do the same thing. We're going to mark off our partition numbers, which for this one is only negative 15. And then we're going to plug in test values to each interval. All right, so negative 15, we want to plug in something to the left. Negative 16 works fine. Negative 15, we want to plug in something to the right, and even though it's not very close, I can plug in 0, and I'm going to do that. And we're plugging them into the second derivative, because that's what we're checking. We don't want to plug them into the first derivative, because that's going to tell us increasing or decreasing. We want to plug in to the second derivative. All right, here's our formula for the second derivative. Plug in negative 16. We got 6 times negative 16 plus 90. And if you do that out, you'll get negative 6. All right, what do we care about? We don't care about the number specifically. We care that it's negative. Now, when we plug in 0 for x, that's the best we can do as far as the easiest way to plug in because we have just 90, and that is positive. Now, as far as relating this back to last section, this is where we would have labeled stuff as increasing or decreasing, but now we have new words. All right, so to the right, where we have the plus sign, it's concave up. And to the left, where we have a negative sign, it's concave down. Just like with the intervals of increasing and decreasing, we don't include the endpoints, so we always have parentheses for their intervals. Same as last time. And so we'll go ahead and write this part down. Our answer for concave down. We go all the way back to negative infinity up to negative 15. And for concave up, from negative 15 up to infinity, nothing stopping us from going to the right. All right, now this is what's often, I think, confusing about these problems is especially the way you read it. It says compute all inflection points. It makes it sound like you should do this first, but you should do this last, because you have to figure out where it's concave up and down first anyway, because you have to see where it switches signs. Right, and we said that negative 15 is our only potential inflection point because it's the only spot where it might change signs, and it does. It switches from negative to positive. So since concavity changes at x equals 15, negative 15, there is an inflection point at that point. Now, usually we want to write inflection points as x and y coordinate pairs. So if you want to figure out the y value, what you have to remember is it's on the graph of the original function, so we have to plug in negative 15 to the original function. All right, so negative 15, our original function is x cubed plus 45x squared. We get negative 15 cubed plus 45 times negative 15 squared. And let's just do that with our calculator. Oops, forgot my parentheses. Negative 15 to the third power plus 45 times negative 15 to the second power. And it's pretty big, 6,750. So our answer here is the coordinate pair for the inflection point negative 15 comma 6,750. Now, one thing I would definitely say is if you had to graph, if you tried to figure out what an inflection point looks like by graphing, one thing is, I haven't shown you what it looks like yet, so it might be hard to do it that way anyway, but this is not an easy value to try to find. And your calculator doesn't just find inflection points for you. Right, but what I'm going to do is graph the function x cubed plus 45 x raised to the second power. Now I know where the inflection point is, so I'm going to adjust my window. The x value is negative 15, so I'm going to be between negative 18 and negative 12, just so I don't have to see too much of it. And then the y value is 6,750. So all I'm going to do is between 6,700 and 6,800 for y. And then I'm going to graph. Actually, this might be too steep. I should have graphed this beforehand. All right, so zooming out a few times gives me this picture, but it's a little too steep, so I'm going to make a better picture for you. Actually, it's very easy to figure out the graph of y equals x cubed has an inflection point at x equals 0. Just do the second derivative, and then you can fill your chart out. And then I want to show you what happens at x equals 0. Right, so right here at x equals 0, which happens to be also at y equals 0, the origin, there's an inflection point. Now what's happening is it's increasing the whole time, so it has nothing to do with that. But what's happening is down here, it's like bending down. Kind of think about trying to make the curve with your hand. You have to bend and wrap your hand down. You can't wrap it up because then, you'd have to have this is one of those things, I guess it would be really useful if I could show you in person, but I'll find a little video to show you. But the way you wrap your hand is it's bending down. And then also if you try to wrap your hand on the right side, it's bending up. Okay. So that's really where inflection points occur, is it tells you where the graph changes, where it's the way it's bending, from bending down to bending up, or bending up to bending down. But like I said, I'll find a little video and link it with this lecture video so you can see it more clearly. Actually, and your book does a great job. I remember looking at the book before. It does a great job if you want to look at the book in this section of trying to explain concavity. Right, but what I really like to do, building from that, is make a little chart, because whether the graph is increasing or decreasing and concave up or down, they don't need to interact at all, as we saw with the y equals x cubed. The concavity changed, but the graph was increasing the whole time. And I just think this is an important picture for everyone to see. So I'm going to make 4 options here. The top is going to be talking about the first derivative. The first one will be where it's positive and where it's negative. And then the vertical side, this will be about the second derivative. The top one will be where it's positive and where it's negative. What I'm going to show you is what the picture of each one looks like. And these are just very general shapes, but they'll all make the same shape. Right. It's also useful to write down what this means. The derivative being positive, first derivative means it's increasing. If it's negative, it's less than 0, that means it's decreasing. And then the second derivative is concavity, but instead of using the word concavity, just talk about what I did before. When it's concave up, it's bending up. When it's concave down, it's bending down. All right, so this first one here, what does the graph look like if it's increasing and bending up? It actually looks something like this. So in order to be increasing, it has to be going up as we move to the right. Bending up, think about, once again, grabbing it with your hand, trying to trace that shape with your hand. Your hand's going to be bending up, your palm is going to be up, not down. Now the next one over here, decreasing but also bending up. I always find the off ones the most challenging for when you're learning this. If it's decreasing, that means as we move to the right, it's moving down, but it's also got to be bending up. Well, that's actually looks like this. It looks like this flipped over. If this was the y-axis, flipped over the y-axis. Well, as we move to the right, it's moving down, but once again, if we try to trace this shape with our hand, we have to have our palm pointed up. Our hand is bending upward. And then for the bottom two here for bending down, if it's increasing, that means it's moving to the moving up as we move to the right, but it's bending down. That means it's going to look like this. And so if we try to trace this shape with our hand, the power palm is going to be looking downward. If we try to grab something, we're grabbing it below. That's also a good way to think about it. If we wanted to try to grab something, we'd be grabbing something below, not above, if this was our hand. And then this stuff, the thing we've been trying to grab it would be above the graph. And then the last picture, if it's decreasing, once again, it's moving down as we move to the right, and it's bending down, it looks something like this. I actually really like that grabbing thing. I never even thought about that till now. But each of these pictures, if we tried to grab something, if this was our hand, we're grabbing above. That's why it's concave up. And then the two bottom pictures, if we were trying to grab something and this was the shape of our hand, we'd be trying to grab something below us. So it's concave down. But it's in general very hard to just look at a graph and see exactly where an inflection point is. You can really guesstimate it pretty well with most examples from a graph, but you will have a hard time just getting it perfect. All right, so the first one isn't really necessarily a homework problem, but I like to do this one anyway because of what the graph is. So it says for the following functions, same directions, find the intervals on which the graph is concave up, concave down, and list all the inflection points. All right, so this first one here, the reason why I like this is the graph of a line, like y equals mx plus b. And as you know, a line is not bending, it's a straight line. So when we try to find all this stuff, we need to compute the second derivative because it's talking about concavity. Now, if doing the derivative of this thing with these letters bothers you, imagine if they were numbers like 2x plus 4. The derivative of 2x plus 4 would be 2. But now our 2 is being replaced by m. So this is just a number times x. The derivative of this part is a number. And this is just a number. The derivative of a number is 0. So the first derivative is 0. And then the second derivative, the first derivative is m, which is just a number. If we do the derivative of just a number, we know we get 0. And what this means when your second derivative equals 0, it does mean there's no concavity. There's no points of inflection. It's not bending. There's just nothing happening related to the second derivative. So like I said, this isn't a homework problem, but you know what the graph of a line looks like, so it also helps to understand that you have to have this bending nature. All right, second one will be more like the previous one we did. We'll have to do some work here. So we want concave up, concave down, and what does it say about the points of inflection? List them all. Okay, so it probably wants an XY pair. Well, all this stuff is telling us do the second derivative. And this is an example specifically chosen that if you were to do the first derivative, you actually would not be able to solve the equation that comes out. Right, so we have to do the first derivative here, but we can see we just need to do the power rule everywhere. The derivative of negative t to the 6th is negative 6t to the 5th. the derivative of 18t to the fifth, bring the 5 down. 5 times 18 is 90. And then subtract 1 from the power. The derivative of 18t is just 18. And the derivative of 17 is 0. All right, but solving this is actually impossible. By hand, you would have to use a calculator if you set equal to 0. That's a good indication that you need to do more. But we do need to do more. We need the second derivative for all that stuff. So do one more derivative. Derivative of negative 6t to the fifth is negative 30t to the fourth plus 90t to the fourth, that derivative. We get 360t to the third. And the derivative of 18 is 0. And now we do exactly what we did before. Set it equal to 0 to find the partition numbers. And then I'll just make a note here. If you did have a fraction, you'd set the top and bottom equal to 0 to find the partition numbers. Just like we did last section with the first derivative. All right, so we got 0 equals negative 30t to the fourth plus 360t cubed. Solve this. Now you can factor out quite a bit here. There's a 30 in common. And if you want to take the negative out, you can, but I'm not going to worry about it. And there's also a t to the third power in common, the smallest power of t. So when we take out that of the first term, we're left with negative t. And when we take out the 30t cubed in the second one, we have just the 12 left. Right now we're just solving an equation. Set each part equal to 0. And solve it. Now the one on the left, you should be able to very easily see that t is 0. But if you need to take a couple steps, of course, do that. I'm just running out of room here. And the one on the right, if we add t to each side, you get t equals 12. Once again, these are potential inflection points. They are not guaranteed to be inflection points. So we must make a sign chart now. All right, our two numbers that we need to plug in to the second derivative, or not the two numbers we need to plug in, the two numbers we need to put on our number line are 0 and 12. And then we want to plug in numbers in each interval to check what sign it is. So we can plug in -1, we can plug in 1, and we can plug in 13 to the second derivative. All right, and our formula for the second derivative is here. We plug in -1, we get -30 times -1 to the fourth plus 360 times -1 cubed. And what does that come out to? Let's see. Got -30 times -1 to the fourth plus 360 times -1 to the third. We get -390. And what's nice about, or what's important about that is that it's negative. Now we want to plug in 1. Don't need a negative sign for 1. And if we plug in 1, this one's not as bad to do by hand, but let's just go ahead and put it in the calculator real quick. Press second enter and get rid of these negative signs. We get 330. What's important about that is that it's positive. and then plug in 13. Do the same shortcut, just copy it, and then since I want to put a 3 right there, just hit second insert, and then you can hit 3 and it'll let you plug it in right there, or you can type out the whole thing. And that is a very large negative number, negative 65,910. But it doesn't matter how big or small negative it is. What matters is that, excuse me, it is negative. All right, so where we have negative signs, that's where it's concave down to the left of 0 and to the right of 12. And it happens to be concave up in the middle. All right, so our answers for that part, concave down, we got negative infinity up to 0. And we've got 12 to infinity. For concave up, that's in between 0 and 12. And then you notice that, once again, both of these are actually inflection points. These are both in the domain because this is a polynomial, so everything's in the domain. So there are inflection points at x equals 0 and x equals 12. But you also want their y value. Well, you might want their y value. So we have to plug into the original. Remember that. If you plug in 0 to the original, I guess I should use t since that's the letter we're dealing with, not x. If we plug in t to the original, or sorry, 0 to the original, we just get that 17. All this other stuff will be 0. But not so nice with 12, so let's plug in 12 to our original. We got negative 12 to the 6th plus 18, 12 to the 5th minus 18 times 12 plus 17, and a huge number. Definitely wouldn't want to try to do that by hand. 1,492,793. And you could not imagine trying to find the inflection point on this graph. And just from this number being so big, I would guess it's like the other one. It's so steep that you wouldn't be able to see it. Okay, so sometimes the inflection points, they only want the x or t values, and this might be one of those. Sometimes they want the coordinate pairs. Just remember, with inflection points, the same as maximums and minimums, you must plug into the original. But that is our second derivative and what it's used for.